I will start it off. So thank you so much, everyone, for joining us today for our program with Anna at the Michigan Science Center on Frostology. And as we were saying before, Anna's going to be doing some experiments that sometimes we can't do at school because they use different materials. So I want to hear the story about how you were able to get them to your house. And we're going to learn about frost and properties of matter and different experiments that Anna can do safely at home. And maybe she'll even show you something that you can do at home. So here we are, Anna. So I'm going to turn it over to you. And what we're going to do, ladies and gentlemen, is we're going to stop a couple times and have questions. So if you can chat in the chat box and respond to Anna, but we're going to hold our questions until we stop for a little bit, and we'll have 2 opportunities for questions. So over to you, Anna.
All right, thank you. So thank you guys so much for having me. I am coming to you from my basement this time, but I actually do work at a place called the Michigan Science Center. So if you are familiar with the state of Michigan, it's actually a state in the United States. And this is where the Science Museum is located. We're in a city called Detroit. It's a pretty large city. And it's one of my favorite museums that I've ever been to. I'm very, very lucky to work there. Today we're going to be talking about a program that we call Frostology. And we'll be answering a couple really interesting questions. Let me see if I can share my screen with you. There we go. All right. So this is a map of the state of Michigan. Now, this big blue shape, that is the state of Michigan. So if you're familiar with a map of Canada and maybe the United States, you might know where the Great Lakes are located. Michigan is actually surrounded on all sides by the Great Lakes. Now, we call Michigan the Mitten State, and you might be able to tell why. If you look at our lower peninsula, this southern half of the state of Michigan, if you hold up your hand and kind of look and keep your thumb separate, but keep the rest of your fingers together, you kind of make the shape of a mitten, and it looks just like our lower peninsula. Now, I'm pointing this out because we're going to come back to this map of Michigan a little bit later on in the program. I see a couple of really good answers. People already pointed out that it looks like a mitten. And you guys even know a lot of the Great Lakes. So a lot of the Great Lakes share a border with Canada as well. And so over here, to the west would be Lake Michigan. We would have Lake Huron. Over to the east, Lake Superior, way up north. But we'll show you another map of Michigan a little bit later on. So really keep in mind this shape. We have our lower peninsula, which we call the Mitten State, and our upper peninsula, which borders Canada. So this is a picture of the building where I work, and that little yellow star down in the corner, that is the city of Detroit, where I am normally located. But right now I'm a little bit outside the city, coming to you from my old house. Now this program, so I see a question that says you can't see the map. Could everyone tell me in the chat right now, are you able to see the screen that I'm sharing? You could say yes or no. Tell me yes or no, can you see the slide that I'm sharing? It says Michigan Science Center. It has a blue map. I'm seeing some yeses. And so if you're having some trouble seeing, I would either try to refresh your page, or you could always exit the meeting and come back. Should be able to see it. It looks like most of our other attendees are able to see this slide. I can stop the share and then put it back up. Let's see if that helps as well. Stop the share, pull it back up. Hopefully maybe you'll be able to see it now. If not, maybe hop in the Q&A section and Molly or Katie can try to help you see the slides a little bit better. All right, so this program is called Frostology. We call it Frostology because we are going to be answering this very important question. The question is, what happens to atoms and molecules when they're exposed to cold temperatures? We'll be talking about some really, really cold stuff today during our program. So cold that you definitely won't be able to try some of these experiments at home, because some of the supplies and equipment I'm going to use would be pretty difficult to purchase. So we're going to talk about this all during our program today, to experience something we might not get to experiment with at home. So keep in mind this question: what happens to atoms and molecules when they're exposed to cold temperatures? So outside where I live right now, it's actually pretty warm. We did just get a really big snowstorm Friday night, and so we actually got almost an entire inch of snow, even in March, which is pretty crazy. We don't normally get a lot of snow in March here in Michigan. I know some parts of Canada probably still have some snow. So tell me in the chat right now, what is the weather like where you live today? What is the weather like where you live? You could tell me the temperature. Tell me what are the conditions like. Is it sunny? Is it cloudy? Is it warm? Is it cold? Is it rainy? Go ahead and tell me in the chat so that I know what the weather's like where you live. See, wet and cloudy for some of us. Snowy but warm. I've experienced that a couple times here in Michigan. We get that quite a bit where it's snowy, but it's also pretty warm sometimes. It's -1. We're 0 degrees, cloudy, 8 degrees, and sunny. It's windy where some of you live. Snow is everywhere where you live. Oh man, so our snow is finally melted. I think we're about done with snow here in Michigan, but I know some of you are a little bit further north than we are, and your snow will last just a little bit longer. I personally love the snow. So I'm seeing a few of you that have snow on the ground, a lot of people saying it's cloudy, a lot of people saying it's sunny, but it doesn't sound like it is. Oh, I almost spoke too soon. I was going to say it doesn't sound like it's actively snowing where anyone lives right now, but it says Sarah got 1 foot of snow yesterday. That's a lot of snow. So we are going to actually be making snow right here in my studio. Now, normally if we were doing this program with the classroom, we'd have your class do this experiment with us. But this is a material that you might not be able to find at the grocery store, but you would be able to purchase it online. We call this one Insta Snow. So we'll be making snow right here in my basement studio using a chemical. So this chemical we call Insta Snow, and I have it right here inside this cup. So I see a couple of people saying it's glitchy. If everyone's having trouble seeing me, definitely let us know in the chat. We want to make sure everyone's able to see. But I have that Insta Snow. It's this white powder right here inside this cup. Now this is what we call a polymer, meaning it's made up of long chains of molecules that have some very interesting properties. Polymers can be very, very different. One example of a polymer is rubber. Plastic is another. If you've ever made slime, that's another great example of a polymer. And so it's basically just made up of long chains of molecules, and they can all behave pretty differently. We call this one Insta Snow, and you're about to find out why. So I'll zoom in just a little further on my cup. And what I'm going to add is just a cup full of water right into this cup that's containing our Insta Snow. And then we're going to make some observations. Let's see, I'll pour in our water. Let's observe what happens to our Insta Snow. Something is starting to happen. Tell me in the chat, what do you see? Snow, that's right. It looks just like snow. This polymer, that white powder, is starting to grow and expand and turn into snow. Now, to you guys across the camera, I know this looks just like snow. It's white and it's fluffy. It kind of falls down and is very, very soft. But this stuff is not made out of the same stuff as the snow we would experience outside, like Sarah is. This stuff is not frozen. I can't have you feel it over the camera, but I can let you know how this snow feels. So this snow is not as cold as snow outside. It's actually pretty warm. It's about the same temperature as the water that I poured into the cup. You'll also notice that even if I were to try to pack this snow together into a snowball and really squeeze it really hard, it doesn't really pack together. So even though water is an ingredient in this Insta Snow mixture, it's actually not frozen, so it doesn't have that ability to stick to itself and form a snowball. If I squeeze it really hard, it actually starts to feel wet. So this Insta Snow is basically a bunch of tiny little sponges. When that polymer touches water, the molecules actually rearrange themselves. They flip back and forth, and they grow up to almost 100 times their original size, which is why it grew out of the cup and spilled over onto the tray. So this stuff is not real snow. This is the stuff that they would use in movies. If they're filming a movie about winter time, movie stars really don't like to stand outside in the cold. And so they use this Insta Snow to make it look like it's snow, especially out in California where they film a lot of movies. Even when it's not winter time, if they want to make it look like it is, because to you guys on the camera, you told me that it looked like snow, and so this is really great for that purpose. But it's not made out of the same stuff as outside. So we are probably familiar with the water cycle. So if you're familiar with the water cycle, we know that that's what gives us most forms of weather here on Earth. We know that water from the ground can evaporate and head up into the sky, where it can then form clouds, and then those clouds will give us different forms of precipitation. Precipitation can be rain, it could be snow, it could be hail, it could be fog, and so that's what gives us different types of weather or snow here on Earth. But we're going to talk a little bit next about how we get our seasons. So we're going to try to talk about how we get our seasons, but I think I might need to pull up this picture since I can't use my virtual background here. Let's see. We'll be talking about our seasons. Now, you can tell me in the chat right now while I pull up my next diagram, tell me, why do we have different seasons here on Earth? Especially Canada and the United States are pretty far north from the equator. So if you know why we get different seasons here on Earth, go ahead and tell me that in the chat.
So we have Maria that says Earth spins, the sun, Gibblers, Earth tilts.
It sounds like you guys are on the right track. So I've got my diagram up now. Let's see if I can go back to our meeting and share my screen. Here we go. This picture actually moves, which is a really great way to talk about the things that you are telling me right in the chat. So you know how we get our seasons here on Earth. It's all to do with Earth's tilt. So this is a diagram of how the Earth orbits around the sun. So as the Earth travels around the sun, we call that Earth's orbit. It is constantly orbiting the sun. It's just doing that very, very slowly. So in this diagram, it's going around once about every 5 to 10 seconds, but really it takes Earth 365 days to make a complete orbit around the sun, and we call that 1 year. We know that over the year that we have different seasons, especially where we live in the northern hemisphere. So if you look at this line that goes across the Earth, you'll notice that there's a tilt. Earth doesn't spin straight up and down like a top. It actually spins on its side, or about, it's tilted to one side. Now you can see that the seasons are labeled in this diagram as well. So we live in the northern hemisphere, the top part of that spinning Earth. So in winter, you'll notice that our side, or our northern hemisphere, is actually tilted away from the sun. That causes our days to be shorter, and it makes it a little bit colder since we're farther from the source of the sun's heat. But in the summer, we're tilted towards the sun. We have longer days, we get more sunlight, and since we're closer to the sun, we get warmer weather. In autumn and in spring, we are kind of in that middle ground, right? Our seasons are changing. We're transitioning between winter and summer, and so our weather is a little bit more mild. It's somewhere in the middle because our tilt is about halfway, and so we're not tilted completely towards the sun like in summer, or completely away from the sun like in winter. So that is why we get our different seasons. So So we have a diagram, another diagram that I can share with you. Let's stop this share. And I want to show you another picture. So here, do you remember what this picture might be? This picture right here on the left. Tell me in the chat, what is this a picture of? Oh, I see a great answer. We see the Great Lakes. Thanks, good answers. That's right. This is a photo of Michigan. So this one is not a map like in the first slide we showed you. This is actually a real photo of Michigan taken from the International Space Station. So as the astronauts on the space station flew over Earth, going really, really fast, they snapped a picture of Michigan at exactly the right time. So we can see all the Great Lakes that surround Michigan in this picture. Here's Canada, here's Ontario right here. And I know some of you live there, and we can tell what season this picture was taken at. So tell me in the chat, what season was this green photo taken in? Yeah, that's right. This is summertime. You can see we've got lots of green grass and vegetation, even have algae blooming in the lakes, which only happens when we're getting lots and lots of sunlight and lots of warm air. But the picture on the right was taken at a different time. Can you still tell that this is Michigan? Still kind of see the outline of the mitten down here. This is Lake Michigan. There's Lake Huron, but we're almost completely hiding our Upper Peninsula and Lake Superior. So that is still Michigan, just taken at a different time of year. So this photo was taken in the wintertime. So today we're going to talk about what happens to our atoms and molecules as we experience cold weather or expose things to really cold temperatures. What I'm going to be using today to talk about cold things is something called liquid nitrogen. So liquid nitrogen is extremely cold. In Fahrenheit, it's about negative 321. And so in Celsius, I think that's about negative 196 degrees. It's extremely cold stuff. And so for this, I'll need to put on a little bit of safety equipment. I've got some safety goggles here just to protect my eyes in case any of this liquid nitrogen were to splash up. And I also have a very special pair of cryogenic gloves. So these gloves have lots of layers of insulation on the inside, and so they're going to protect me if any of this really cold liquid nitrogen were to get on my hands. It will protect me, and so I won't get frostbite. My hands will stay very safe. And so go ahead and I'll put on my gloves. And first, I'd just like to show you what this liquid nitrogen looks like. And I just filled my Dewar, but I left it on the side, so I'll go grab it. Now I know Molly and Katie were curious about how we transported some of these materials to my house. So obviously if I were to transport our liquid nitrogen in this small thermos, it's not really very large. It wouldn't be able to bring very much home. So I was actually able to fill up our bigger Dewar, this thing right here, which is basically the same thing as a thermos. It's a vacuum insulated container that we filled with liquid nitrogen, so I can transport about 6 liters of it back to my house, which is enough to do a few of these Frostology programs before I run out. And so then we'll have to see if I can head back to the Science Center to refill. So this is a Dewar. It was invented by a guy named Dewar. So he actually came up with the idea of how to keep liquid nitrogen or other things really cold. But he forgot to patent his ideas. Patenting is very important in the world of invention, because if you don't patent your ideas and claim that they're your own, then people like Thermos can take your ideas and sell them on their own. And so Thermos is much more famous. They make a lot more money than Dewar does, but it's actually the same exact technology. So I have some liquid nitrogen here inside my Dewar, and I'm just going to pour some down into this glass Pyrex beaker. So This is made of Pyrex glass, which means that it is borosilicate glass, and it's going to be really resistant to changes in temperature. So you can't pour liquid nitrogen in just any container because it is so cold it can cause that container to crack or to explode, like I'm seeing in the chat. So this container is designed for holding things that are extreme in temperature. So you can make this glass really hot and then really cold. And so it's not going to shatter because it's made out of special glass. I see a question about how do you spell Dewar, and it's actually D-E-W-A-R. So that is the name of the scientist who invented it, D-E-W-A-R. Good question. All right, so we'll pour some liquid nitrogen right here in the Pyrex. And I want you to just take a look at what is happening. So if I put my glove on, you might be able to see it better if I create some definition. Do you see any movement inside the glass? Tell me. What do you see happening? What would you call, oh, we see some steam. That's a great observation. There is some steam coming off the glass, and we see some frost starting to happen. Now the liquid nitrogen, do you see those bubbles that are forming inside? I know as the glass fogs up a little bit, it makes it a little trickier to see, but hopefully when I first poured it in there, you were able to notice that this liquid nitrogen is bubbling, that bubbles are forming. Now, if this was water and I had put this glass on the stove, what would you call that process? What would you call what's happening to the water when you put it on the stove and it starts to bubble? That's right, that it's boiling. Great answers, you guys. Boiling is a phase change. So we're going to talk next about our states of matter and how they relate to this liquid nitrogen. So if we talk about our states of matter, mainly there are 3 states of matter that exist here on Earth. There are a few more, but when we're talking about liquid nitrogen and talking about the water cycle, we can stick to these 3 states. First, all the way here on the bottom, we have ice cubes. So this diagram is using water, not nitrogen necessarily. This is using water to talk about the states of matter. What state of matter would you call an ice cube? It is, yeah, see lots of great answers. Solid. That's exactly right. We would call ice cubes a solid. We can see that the molecules inside, the H2O molecules, which they're showing as these small blue dots, these little blue dots are the water molecules. They're packed extremely close together. They don't have a lot of energy. They're only just barely wiggling back and forth with the small amount of energy that they have. But we can always change our states of matter. The easiest way to do that is by adding or taking away energy. If we add some kinetic energy, some energy of movement in the form of heat, we can actually melt our ice cubes. So melting is a phase change where our solid ice cubes turns into what state of matter? That's shown right here. It is a liquid. You are exactly right. So ice cubes can melt into a liquid by adding heat, which is kinetic energy. Now we see that the molecules are a bit more spread out in this diagram. But if we add even more heat or kinetic energy, we have evaporation, or what you called boiling, which is the same thing. So if we boil a liquid, it turns into what? A gas, exactly right. And those molecules are even more spread out. They've got a ton of energy, and they're really bouncing around the room. Whereas we can keep our liquid in this container, that boiling gas will expand to fill whatever space it's in and keep going. So those are our states of matter, and this process is reversible, right? We talked about we can have precipitation where our clouds or our water vapor can rain or snow and turn back into liquids or solids just by making those things cold. So keep in mind, these atoms and molecules are moving around.
Gabby, come back down, try again.
If you are in the chat, make sure you keep yourself muted just because everyone in the chat or everyone in the meeting can hear you as well. Thank you. Now, this liquid nitrogen we saw was boiling. So even though I haven't put the beaker on the stove, boiling is just a phase change. Liquid nitrogen has to be negative 321 degrees Fahrenheit or negative 196 degrees Celsius in order to be a liquid. If it gets any warmer, it immediately starts to boil and turn back into a gas. So that's happening right here at room temperature. We don't even need to add any heat really, other than the heat that's in the air all around us. To prove to you that this liquid nitrogen is in fact boiling at room temperature, I brought with me this very scientific piece of equipment called a tea kettle. Now, maybe you've used a tea kettle before. You might be familiar with what sound a tea kettle makes when you put it on the stove. So I poured a little bit of liquid nitrogen inside. We'll add just a few more drops. And then we're going to seal the lid. So if you know what noise a tea kettle makes when it's boiling, give it a listen and tell me, what do you think? Good answer, Christian. I couldn't have spelled it any, or Tristan, I couldn't have spelled it any better myself. Right, we know that that whistling noise happens because that gas is expanding inside the container. Water will expand as it boils, just like what liquid nitrogen does. And when you close the lid of the tea kettle, all that gas is forced to escape out of that tiny, tiny hole in the lid, which makes a whistling noise. Just like you can make a whistling noise with your mouth by pushing your lips really close together and only giving the air a very small opening to go out. That's exactly what happens here. So that stuff really is boiling. Now, liquid nitrogen has an expansion ratio of about 700 to 1, meaning it takes up 700 times more space as a gas as it did when it was a liquid. And so we can actually use that to do some very interesting other science. Now, normally I use dry ice for some of these demonstrations. We can't get dry ice sent to my house, so that is one supply that I'm missing, but liquid nitrogen actually has a much larger expansion ratio than dry ice does. So this experiment should work even better, but we'll find out. So I'm going to pour just a small amount of our liquid nitrogen down here into this flask, and then I'll put the lid back on, so all of that expanding air has to come out the end of this tube. I pour a little bit of liquid nitrogen down into the flask. Get on safety glove here. Just a little bit, because we said that this stuff is expanding very, very rapidly. We see that fog, and that's actually not nitrogen gas. Nitrogen gas is invisible, but since this stuff is so cold, it's actually condensing the water vapor in the air and turning it into clouds because it is so, so cold. All right, let's see if we've got any movement coming out the end of our straw here. So we can actually create, just powering it with the expanding liquid nitrogen, we can actually create a big pile of soap bubbles. So we're actually filling those bubbles with that nitrogen gas. We can make this one in the front really, really large. Just using that few tiny drops of liquid nitrogen, look how much gas we've actually created. So I have one other demonstration to try with this, and that's trying or attempting to create an explosion using liquid nitrogen. So this liquid nitrogen, we said, is going to expand at an extreme rate. But if we trap that gas inside a closed container, so something that's completely closed, not like the end of this straw, and give that gas nowhere to go, we can actually create an explosion. So we can actually, we'll use this as our closed container. So we've got an empty coffee canister here. I've poured just a tiny amount of water in the bottom, which is going to help that liquid nitrogen evaporate even faster because the water is kind of warm. And then we're going to have to try to very quickly pop on the lid. Now, we said that this stuff expands really, really fast. And so we'll have to see what kind of luck we get with trying to get this stuff to pop the lid. So just a couple drops in there. We said even a couple drops will expand to up to 700 times their original size. And there is our explosion, right? So we normally think of explosions thinking about fire or thinking about combustion reactions or things like fireworks. But you don't need to have any fire to have an explosion. All you need is an expansion of gases inside a closed container. Do that one more time. Always when you go to check on it that it goes off, right? Ta-da! All right. So that is the expansion of our gas, right? So if we think back to that diagram of our states of matter, right? We know that as things start to warm up or we turn things from being a liquid into a gas, they start to take up way more space. So I have two last experiments for us to try using our liquid nitrogen here. This is a good time for us to pause for questions. So if you do have any questions that you might like me to answer, go ahead and type them in the chat. I'll give you a moment to type your questions if you have any while I set up our next experiment.
Thanks, Anna. That's great. And Tristan, I'm so glad that you were shocked by that experiment and that it scared you a little. That's okay. I think Anna addressed the safety, that she's wearing goggles and she has those cryogenic gloves, which is a big word, which means that the liquid nitrogen won't hurt her. Okay, so if you'd like to put your questions in the chat, Gibbler wants to know, how does nitrogen compare to other gases?
Nitrogen is actually a really important gas here on Earth. So nitrogen actually makes up over 80% of the air that we breathe. So it's all around us here on Earth. We just don't notice it because it is invisible, but it's all around us all the time. The important thing about nitrogen is that if you wanted to make it into a liquid so that we're able to see it, it does have to be extremely cold. Negative 196 is cold enough that if it were ever that temperature outside, we would get frostbite all over our bodies. It's extremely cold, way too cold for humans to exist at that temperature. But nitrogen, we call it liquid nitrogen because it really is just nitrogen in a liquid form, and it has to be that cold.
That's a great answer. Thank you. So Tristan would like to know, if you pour liquid nitrogen on a solid and break it, what is it now?
So the liquid nitrogen, after you pour it on a solid, will probably evaporate away and go back to its state as gaseous nitrogen in the air around us. The item that you broke only underwent a physical change. So if you've ever seen on YouTube where people will freeze things like a basketball and smash it on the ground, it's still a basketball, right? You've just broken it into tiny little pieces of a basketball. So there's been no chemical change that happened to that basketball. You've just broken it into tiny pieces by taking away its elastic properties. Unfortunately, freezing a basketball takes a great amount of liquid nitrogen, more than I'd be able to transport home with me. But there are lots of really awesome YouTube videos that you would be able to find if you look up liquid nitrogen smashing things. So you can smash things like flowers or basketballs or other kind of soft objects, and they're very, very cool.
Great question. A great answer too. I like that. But we can't try that at home. And thank you, Tristan, for saying you feel smarter now. So do I.
Chris, yeah, so it'd be difficult to try any of these experiments at home because liquid nitrogen is not something that you can purchase at the store. The Michigan Science Center, since we are a science museum, we have it shipped to us in a giant container that's taller than I am and much bigger around. It's extremely heavy, but it's normally used for welding. So if you know someone who does welding, you know that that's very, very hot, right? Since you're trying to melt two metals together, they actually use liquid nitrogen to cool down welding reactions. And so it's difficult to come by. Not everyone's allowed to purchase it. You have to be using it for either for work or for science.
And that answered Christiane's question. So thank you for that question and answering in anticipation. And Weston would like to know, how does the sky create snow?
Great question. So I'm going to put up that slide again of our states of matter here really quickly. And so we said that these arrows basically just represent phase changes. So if we add heat to a liquid, right, we can make it evaporate and turn into a gas or a water vapor up in the sky. But as water vapor travels higher and higher, the temperature starts to go down. And you also you have changes in pressure. And changes in pressure are what give us most of our weather. So we can change our states of matter not just by temperature, but also by pressure. And as that happens, this water vapor, the gas up in the sky, will condense back down into a liquid. So it'll turn into raindrops, or it can turn into fog that we see close to the ground, or if it's cold enough, when those water droplets form way up high in the sky, they can freeze and turn into snow.
That's awesome. So just Declan wants to know, in addition to the snow, how does the sky make hail?
Ooh, same process. So if you form large enough water droplets and the temperature changes so dramatically, you can actually freeze them solid. So depending on where you live, you might get hail every so often. We get hail here in Michigan sometimes, and sometimes it can be almost the size of a golf ball. So if you've ever seen videos, hopefully you've never experienced golf ball sized hail at home because it's very, very dangerous. But if you've ever watched videos, you can form hail so large just by freezing those water droplets forming up high in the sky that they actually rain down and they can, break windows or dent cars. So if you ever see hail starting to come down that's pretty large, you should definitely take cover and stay away from it because it can be very dangerous.
Okay, and maybe we'll take one more question before we go on. George would like to know what happens when liquid nitrogen turns into a solid, or can it be?
It can turn into a solid. There's a pretty interesting experiment that a college, I'm not sure which college, had done, but they actually put liquid nitrogen in a vacuum container. Now, it's not possible to create a low enough temperature using any standard lab equipment that we can freeze nitrogen into a solid, but if you take a vacuum chamber, something where you can remove all the air molecules from inside, you can actually condense liquid nitrogen down into a solid. So by removing the air molecules from inside, you're actually removing that kinetic energy that we observe as heat, which makes the temperature drop so low inside the vacuum that you can actually create solid nitrogen. It doesn't last for very long because it's highly unstable. If it warms up even a little bit, it'll go right back to being a liquid and then to a gas, just like we see in our states of matter diagram.
So thanks, Anna. We'll go on to the next part of the presentation and have save some questions for after you've part.
Yeah, absolutely. So for this, I'd like to do an experiment where you guys get to make a hypothesis. You tell me what might happen during this experiment. So I'll explain the setup, and then you tell me your hypothesis once I explain what we're going to try. So I have a balloon here, and I'm going to blow up the balloon using my own breath, which is a gas, right? So if you take a deep breath and breathe out, we know that our breath is a gas, at least at room temperature. So I'm going to fill up this balloon with a gas, my breath, and then we're going to freeze the balloon with liquid nitrogen. So I want you to tell me your hypothesis in the chat. Tell me, what do you think is going to happen to this balloon when we freeze it with liquid nitrogen? Go ahead, tell me in the chat. I'm going to blow up our balloon and then we'll get started. I see some great hypotheses. I see that it could pop, it might freeze solid, there might be a big pop and a boom, could turn to plasma. Now that's a great hypothesis. Plasma is another of our states of matter. If you are familiar with lightning, lightning is actually plasma. So that's not a solid, liquid, or gas. It's another state of matter that we experience here on Earth. So that is another great guess, definitely tied to our states of matter. A lot of people telling me that it could pop, that it could explode. We have some very, very great hypotheses. I see someone thinks that the balloon is going to survive. All right. I see some great hypotheses here. These are very scientific answers. So thinking about what we've learned about so far, thinking about our states of matter, let's go ahead and we'll try this experiment. So I'll place my balloon down here in this metal bowl. We'll zoom down on the table. that we can all get a closer look. Put back on my cryogenic gloves. We are going to pour our liquid nitrogen all over the balloon. Here we go. All right, now, I haven't quite heard a pop yet, but we are definitely losing some air from our balloon, right? It's really shrunken down. If you hear that noise, it now sounds really, really crunchy. So if you said that it could freeze, it's definitely pretty frozen. I know you're not able to see it. Let's give it another moment here just to see what might happen next, and then I'll just pull out the balloon so that we can make some observations together. So I see that some people are observing that it's shrinking or deflating, that it's losing air. All of those things are definitely true, right? So we didn't quite hear a pop, but it's definitely lost some air. So let's pull out the balloon and make some observations. All right, so the balloon is flat like a pancake, but let's look at what happens next. You'll notice that now that I've taken it out of the bowl of liquid nitrogen, right? Our balloon is now right back to its original size and shape. It's now pretty bouncy and squishy and full of air again. So let's think about what just happened, right? I saw some great guesses, and we're really thinking about our states of matter. This balloon was certainly frozen. It definitely lost its elastic properties. You heard that it sounded really, really crunchy. But the most important thing we noticed was that it deflated. Now, there's no hole in the balloon. You can see that there's no hole. It's got all of its same air that we started with here inside the balloon. But what we did is we had a phase change. This liquid nitrogen is so cold that it actually condensed my breath inside this balloon and turned it into a liquid. Now, if we think back to our liquid nitrogen, we said that that has an expansion ratio of about 700 to 1. Now, the expansion ratio of my breath is not quite that extreme, but there is some nitrogen in my breath. We said that it's over 80% of the air that we breathe. So there was some nitrogen in my breath, a bit of carbon dioxide, a little bit of oxygen. And so this was actually condensed down into a liquid, which took up much less space. We said that this process is reversible. So if I zoom back down and I set my balloon back inside the liquid nitrogen, right, we can do that all over again. We can just take that breath, make it really, really cold, and change its state of matter into a liquid. Now, you can't really freeze my breath with liquid nitrogen. You'd need, again, one of those vacuum chambers in order to do that, to turn it into a solid. But I would never want to see my solid breath. That sounds absolutely disgusting. But that process is reversible. As soon as the air molecules warm back up, they re-expand the balloon. Now, was anyone a little bit disappointed that we didn't get to pop the balloon today? If you were a little disappointed, like I see Christian was, I see Gibbler was, I see a few people that were kind of disappointed, and I understand that. Popping balloons can actually be extremely fun, so we'll do that next. So we said that this liquid nitrogen expands at a ratio of about 700 to 1. So the only thing we need to change about that experiment is where we put the liquid nitrogen. So instead of pouring the liquid nitrogen on the outside of the balloon to condense the air inside, we're going to pour the liquid nitrogen inside the balloon and let it expand. I'm here in my studio, and so popping balloons, especially with liquid nitrogen, can be extremely loud. The microphone should cancel out the noise for you, so it shouldn't be too loud. But if you thought my popping coffee canister was loud, once you see our balloon starting to grow and expand, you might want to cover up your ears. So I'll go ahead and put on my hearing protection right now. Always, safety first, always. Now we'll be using this test tube and a funnel, and then just a different balloon right here. So I'll pour some liquid nitrogen down inside this test tube. It is boiling at room temperature, just like we saw earlier. Take off my gloves for just a moment so that I can stretch our balloon over the top of our test tube. And you can see that the balloon is starting to grow, but we need to very quickly dump that liquid nitrogen down inside, seal it off so that that balloon starts to grow, and eventually that expansion will become too much and the balloon will pop. All we're left with is kind of a sea urchin looking piece of balloon. I can zoom in on the table to show you. And so all we're left with is a little bit of balloon shrapnel that I think looks like a jellyfish or like a sea urchin. So that is all of the liquid nitrogen demonstrations that I brought to show you guys today. I'm glad your ears were fine. Like I said, I think the microphone cancels it out just a little bit, but just in case, safety first, always.
Well, Anna, that was just incredible. Everybody loved that. So we'll take maybe 3 more questions, and then I want to ask the students a question, and they could maybe help us do some planning. So Rachel wants to know, if you put your hand in a bowl of liquid nitrogen, will it freeze your hand?
Yes, absolutely. Now, your body is about 98.6 degrees. We know that that's like a healthy human temperature for our body to exist at least in Fahrenheit. So if I were to splash liquid nitrogen on me in small droplets, it would immediately evaporate because my hands are so warm. So thankfully we have a small layer of protection. I would never do that on purpose because that wouldn't be very good lab safety. But if I were to submerge my hand down into a bowl of liquid nitrogen, it would freeze my hands just like you would see in those basketball videos. It would give you frostbite really, really badly, which could cause you to lose feeling in your fingers.
Yeah, so that's why we always have to have safety first. What is the coldest temperature required to melt ice? That's a good question, especially for students in the north who have lakes that are frozen and they might want to play on them. So we need to be careful.
Yeah, so it's so ice has to be at there are set temperatures for water to freeze. So in Fahrenheit it's 32 degrees, and Celsius it's 0 degrees. So at 0 degrees you will theoretically have ice, but to make it safe to walk on, I believe that you have to have a constant temperature of below freezing for at least 2 days. You should always test your ice. I'm sure you guys, if you have a lake in your backyard like I do that you use for ice skating, that you always do a check to see how thick the ice is first before you walk on it, or especially before you were to drive on it, if you've ever done ice fishing or anything like that.
Okay, and I guess I'm going to combine this. How is liquid nitrogen created, and is it safe if you ingest it anyway?
Great question. So liquid nitrogen is created in a facility that's making it to be shipped out and sold for those purposes that I talked about. So either for classrooms or for science museums or for welding companies. But they basically take it and put them in these big pressurized containers. So just like we talked about with our vacuum container earlier, they actually pump in nitrogen gas, which is in the air all around us, and then they can just condense it into a liquid. So it's the same thing we've been doing here, but just on an industrial scale. It's not safe to drink. We said that it is extremely cold. Your mouth is a closed space, so kind of like I said, if I were to submerge my hand, if I were to submerge my tongue in liquid nitrogen, it would freeze my tongue. Kind of, if you've ever, I know, hopefully you've never tried this, but if you've ever heard of that you shouldn't lick a flagpole, your tongue is covered in nerve endings and your taste buds. And so if you expose it to something really, really cold, you can actually freeze your tongue and you can hurt it pretty badly. So it is not safe to drink. You definitely wouldn't want to ingest anything that you're using for science, even if it sounds like it might be food.
Right, exactly. So safety always first. Now, students that are out there, we have a science expert with us, and she has set up her whole basement. And what we would like to know from Connected North at Home is, what are some things that you are interested in learning about that are scientific? And maybe Anna can help. And what are you really interested in? Other topics? Because we know that Anna is a scientist.
Yes, and I'd love to talk about some things that
Chemistry.
you are most interested in. I'll give you a heads up that we do have a few more programs booked for Connected North at Home. So we'll be talking about our live animals. So we have a live animal. We have Madagascar hissing cockroaches that we're going to meet during one of our upcoming programs. So we'll talk about zoology, and we'll be talking about animal adaptations. And so we also have a combustion or fire show, I believe we're doing. And then we have an entire show focused on chemistry experiments that you can do at home using materials that you might be able to find in your kitchen or that you could purchase from the grocery store.
Perfect. And we had a couple of students that said that they would like to learn about geology, rocks and minerals.
Okay. That was a great suggestion. I'll have to think a little bit about that one, but I definitely have some ideas in mind.
Okay. So, and biodiversity, I think we'll be talking about that with the animals, and periodic table will be with the chemistry, Evan. We know that that's really cool, and fish and technology. So thank you, students. We really want your input. Center of the earth, volcanoes. We can find something for that. Space, we have things coming up for space. We have an astronaut that's going to speak to us, and an astrophysicist that Anna might even want to join as somebody who's a learner. So thank
Absolutely.
you. And oh, that's a good one. Making safe cleaners for your house. Can we do something in kitchen chemistry about that?
Sure, we can. Yeah, I can try to think about that specifically. About
Dibbler, Chris Hadfield. I hope you don't mind, Anna, but Chris Hadfield is going to do part of a presentation, not live, but with video with our astronauts. So he has given some videos that he can share with them. So do it yourselves. Yeah, actually making slime. Slime is a good one. So thank you, boys and girls. Anna, that was just incredible as always. And it doesn't look any different than your studio back at the Michigan Science Center. So we are so grateful. Maria says thank you. Gibbler says thanks.
oh, thank you so much for joining us, you guys. This has been a ton of fun.
So we can, boys and girls, at 2 o'clock Central and 3 o'clock Eastern, we have an expert about.
Allie, you're muted for some reason.
I can hear you.
Not sorry, my volume was off.
Okay, sorry. At 2 o'clock Central and 3 o'clock Eastern, we have somebody who is an expert on Egypt and mummies and going to talk about hieroglyphs. And then at 6 o'clock Central, 7 o'clock Eastern, we're going to do Zumba again. So thank you so much. Coke and Mentos is something that they might want to learn for kitchen chemistry, Anna.
Oh, okay. I could do that. That sounds like a lot of fun.
That's a great experiment. So thank you, everyone. We'll see you again. Thanks, Anna. Thanks, Katie, and everyone that supports. Thank you so much. Take care. We'll see you later.
Awesome. Now, Anna, the kids referred to you as Jill Nye, the science gal.
I called that one. That is funny.
Thanks so much.
You're welcome. See you later.
Bye, guys.